So we're not gonna do a lot of calculations with buffers. There are quite a few calculations we could do. We do not have quite as much time because of that 2-week snow we had. So, but I do want to go over what a buffer is. If we did a calculation with it, we would use a rice chart to show how the concentrations changed. But we're going to just calculating the pH of a buffer that exists. So first off, I want you to understand what a buffer is. So the word buffer is used in a lot of different fields, and sometimes it actually means a field. So like a buffer zone would be like a land between two things. So in chemistry, what a buffer is, it is a solution. So the implications of it being a solution, it's a mixture. So it's not water. It is water with stuff dissolved in it. Okay. It is a solution that maintains its pH when small amounts of strong acid or base are added. Or other changes occur. So the easiest one to think about is the adding a strong acid or base. I just added the or other changes occur. There are other things that can happen to a solution that could possibly affect the pH, but if it's a buffer solution, it's not going to affect it very much. Okay, so maintain its pH, whatever the pH level happens to be, that is around the range it will stay at. So in your body, there's a lot of different buffer systems in your body that are completely separate from each other. And so the most common one that people might have heard of is the buffer that exists in your blood. So your blood needs to be at a pH range somewhere between like 7.35 and 7.45, something like that. If it goes too low, it is very dangerous and you can get sick or worse. If it gets too high, it's very dangerous. You can get sick or even worse. So what maintains that pH is an equilibrium between carbonate, bicarbonate, and carbonic acid in your blood that are created by carbon dioxide. So carbon dioxide mixed in your blood creates carbonic acid, and then that can break down to bicarbonate and carbonate. So it's actually like a 3-component system. And then other parts of your body, like your stomach has a certain pH that you need to maintain. So if somebody does not maintain that, then you get things like acid reflux or ulcers. Or if it goes the other way, then it's not acidic enough, and then it doesn't work properly to start the breakdown of food. Most of the issues are when it gets too acidic. But still, even though it's really, really acidic, it needs to be at a certain pH because then it starts to mess up other things around it. So the way that this works, the way that a certain pH level is maintained is because it contains a weak conjugate acid-base pair. So anything that is truly labeled as a buffer needs both an acid and a base already present in the solution. So it wouldn't just have an acid or just have a base. It would have a conjugate acid-base pair. And the reason it needs to be weak is because strong acids and strong bases are not going to be in the same mixture as its conjugate. Strong is a one-way arrow. You cannot have it cannot have both. And so if it was nitric acid, it's not going to be in equilibrium with nitrate. Okay. So the way this works, if you add an acid to a buffer that has an acid and a base, if there was no, if it wasn't a buffer, when the acid is added to water, it gives water its hydrogen and forms hydronium. But if you had a base present, the thing that most likely takes a hydrogen is the base. So if there is an acid base present already, if you add acid, then it will react with the base that's already there. And so water will not get the hydronium, so the pH won't go down. If you add base, it will react with the acid that's already present, and so you will not end up with hydroxides floating around, so the pH won't go up. So it tries to keep it in a small range, but it's just small amounts. You can't like dump a lot of it in there because at some point you're going to run out of this weak stuff. So here we have an example. We have 0.250 molar HF and 0.200 molar fluoride. So in order to be a conjugate acid-base pair that's a buffer, it actually has to contain a nearly equal measurable amount. So if we go back here, this is the amount of sulfite that's created. We cannot measure 3.10 times 10 to the negative 4. This is not a measurable amount of sulfite. This would be you actually added the fluoride and you added the HF. It wasn't created by dissociation. It's not X. It's actually been added to the mixture. And so in this pair, which one is the weak acid? So write down right here in this buffer, write down which one is the weak acid and write down which one is the weak base. This identifying and actually writing down which is the acid and base is going to be important for our equation that we use here. Okay. So weak conjugate acid-base pair, the formulas will only differ by one hydrogen. The thing that has one extra hydrogen of the pair is the acid of the pair. And so that would be the HF. And so the weak acid would be the 0.250 molar HF. And the base would be the 0.200 molar fluoride. So the acid will have a Ka and the base will have a Kb. So if you have a buffer, this is part of what we went over in solubility, which is the common ion effect. If you have a common ion effect, your X is going to be lower because you've already got part of the product. And so if you were to do a buffer here, it would be, you would have an amount of this, and your initial concentration of the conjugate would not be 0. It would be whatever was dissolved. So that a chart would look different. But what we are going to use, we can use a chart and we can go through the whole process and do the minus X and plus X, and we would ignore the two minus and plus X's because of how small the constant is. And then we would solve for X, and then we would use that for the pH. But because this is a specific situation where X is not very, very large, they, meaning Henderson and Hasselbalch, and I think there's another person that their name sometimes is attached to these two names already. But there's an equation that is used, and it's what they have done is they have combined the equilibrium expression, the information in a Rice chart, and the pH equation all into one to create one equation that is referred to as the Henderson-Hasselbalch equation, and we only use it for buffers. So in order to use it, you have to know which one is your acid, and you have to know which one is your base, and you have to know how much of each you have. But that's it. And so the equation is the pH is going to equal the negative log of the Ka. So the acid of the pair is the one that has the Ka. So that's why one of the reasons you need to know what the acid is, so you can find its Ka. So our acid is HF for this example. And then you're going to add to that the log of the molarity of your weak base divided by the molarity of your weak acid. And you can also use moles of each because they're in the same solution, so they have the same volume. So molarity is moles over liters. So the liters would cancel because they're the same volume. But this we already have the molarity, so we don't have to convert it. We don't even know how much there is. But moles or molarity work for the buffer because they're in the same solution. Okay, so in order to use this equation, you have to know how much base and acid, and you also have to know which one is the acid and which one's the base. You would divide them, and then you would take the log, and then you would add it to the negative log of the Ka. So here's our example, and it goes along with our HF. So I'm kind of just like slowly working our way to calculating the pH. Calculate the pH of the buffer that has 0.250 molar HF and 0.200 molar fluoride using the Henderson-Hasselbalch equation. And I went ahead and put what the Ka of HF is. This is from the book, but I went ahead and just wrote it down on this example. And so if we plug in all the information, so we're going to do pH equals the negative log of the Ka, which is this number here, 3.5 times 10 to the negative 4. Plus the log of the base, which is 0.200 molar fluoride. Over the acid, which is 0.250 molar HF. So you got to divide these and then take the log, and then you add it to the negative log of this. And then at the end, we're going to round our number to 3 significant figures because our molarity is 3 significant figures. I got a pH of 3.36. The pH of the buffer, the range that it's in is always going to be based on the Ka of the weak acid of the conjugate pair, because you see this is 3.4559. And you want nearly equal amounts of conjugate acid base pair. And if you had an equal number divided by, like one number divided by itself, the log of 1 is 0. And so you want this portion of like the concentrations to be close to a ratio of 1 to 1. And so that would put the pH close to the pKa. So if you, which is the Ka, the negative log of Ka is called the pKa. And so if you wanted something with a pH over 7, if you wanted on the base side, you would want to have a Ka that was to like the -8 or -9 power times 10 to the -8 or -9. You would want a conjugate acid base pair where the base was stronger than the acid. But you can have a pH, you can have a buffer at like all the way down to 1. It's not going to be that good of a buffer because the weak base is really, really, really weak, but it's still a buffer. And you can go all the way up to like 12 or so. Okay, but this is the example. It goes along with this one right here. That is not nitric acid. That is HNO2. That's nitrous acid. Okay. And so the very last question on the homework is a buffer.